All right, so I kind of already did a charge sharing example in the last video while I introduced the concept, but here I'm just going to give like a true example problem. So the problem would say something like, oops, solve for the voltage after the switch closes. That would be the problem, and then the circuit would look something like this. You get a switch that's initially open, two capacitors, right, connected to ground. And let's say that this one is 10 microfarads, and it's initially charged to 2 volts. And let's say that this one is 6 microfarads, and it's initially charged to 3 volts. Okay, so we want to determine what the voltage is on this node. Let me draw the node. This node after the switch closes. So initially they're two different nodes, right? We've got this yellow node here and this green node here. But after the switch closes, let me actually go ahead and take this circuit again. Copy it over here. And, oops. When the switch closes, what we're left with is a closed switch and one node connecting the two capacitors. So this final node in purple, that's the voltage that we're interested in finding. We know the initial voltage. So what do we have to do? Well, what we did in the previous case was we have to find the initial amount of charge stored on the capacitors. So C1 and C2 here. Let's say that QC1 initial is 2 volts times 10 microfarads, or 20 microcoulombs, right? And then QC2 initial is 3 volts times 6 microfarads, which is going to be 18 microcoulombs. So my Q total to start is the sum of those two, or 38 microcoulombs. And I know by conservation of charge that that's my final Q, okay? And so if I know my final Q, all I have to do is solve for my final capacitance, which I know my final capacitance is just the sum of these two, which is 16 microfarads. I can very easily use CV equals Q, rearrange it to say V is equal to Q over C, and I can say V final is Q final over C final, which in this case, this is V final. And I can say that that's going to be equal to 38 microcoulombs divided by 16 microfarads. My micros cancel, and I'm left with 38 divided by 16, which should be, if I know the mental math, 2.375. Let's see if I know that correctly. 38 divided by 16, 2.375 volts, okay? And so that would be the solution to this problem. Oops. Let me actually just grab this whole thing, move it, and then I'll put a big box around it. All right, so we solved another charge sharing example. Hopefully this is pretty clear. Again, I mentioned that this is very important in DRAM memory for sensing sensing the value stored in a memory cell. Very important concept, really kind of gives us a feel for, and what you notice is that the voltage in both of these cases, right? Initially I started with 1 volt and 2 volts in this case, and I ended with a voltage of 1.69, which is between those two values, 1 and 2. And here I started with voltages of 2 volts and 3 volts, and my final value was 2.375. So you'll notice that the voltage should always be between the two starting values. So here it was 2 and 3, like I said. If you ever get a voltage for your final answer that is outside of the initial voltages, you probably did something wrong, okay? So I'm going to leave that here, and this is the last little video on the introduction to capacitors and kind of the overview of capacitors, how they work, what they are. And in the next segment of this module, I'm going to start talking about RC circuits, which are circuits that contain resistors and capacitors. mainly circuits that contain a single resistor and a single capacitor.